In today's class, we are going to talk about voltammetry. Voltammetry experiments investigate the half-cell reactivity of an analyte. Voltammetry techniques measure current as a function of applied potential under conditions that promote polarization of a working electrode. Some of the examples: we have Polarography. It is a type of voltammetry. It employs a dropping mercury electrode, what we abbreviate as DME, to continuously renew the electrode surface. In polarography, the current flowing through the cell is measured as a function of the potential of the working electrode. Usually, this current is proportional to the concentration of the analyte. So it's a sensitive electroanalytical technique that is especially useful for trace analysis. Then we have Amperometry. Amperometry, one of the voltammetric technique in which the constant potential is applied to the working electrode and the current is measured as a function of time. The current is proportional to analyte concentration. So, in other words, voltammetry at a constant potential. Let us just add that the residual current is the slowly increasing current at the foot of wave, which is non-Faradaic in nature. Then half-wave potential is the potential at the midpoint of the wave. Then we also have current is exactly half its limiting value, and it is characteristic of electroactive species, and it's independent of the current of the capillary used to obtain the wave. So this depends on solution composition, change with variation in pH. We have solvents and addition of complexing agent. Generally, as we know, we'll discuss it more further, that application of polarography, that it is effective in qualitative identification of unknown, and then to study the rates of chemical reactions that compete with the electrode reactions. And it is used to determine more than one ionic species in solution, but this requires a series of steps of the same form, which occurs when the discharge potential of each species is reached. So effective in determination of very dilute solutions. That's why we talked of trace when we are doing trace analysis. Current in electrochemical cells. Let us just say that some electrochemical cells have significant currents. Electricity within a cell is carried by ion motion. When small currents are involved, we will say that E is equivalent to IR holds. Then R depends on the nature of the solution. So when current in a cell is large, The actual potential usually differs from that calculated at equilibrium using the Nast equation. So this difference arises from polarization effects. The difference usually reduces the voltage of a galvanic cell or increases the voltage consumed by an electrolytic cell. So polarization, electrodes in cells are polarized over certain current voltage ranges. So electrodes are purposely kept small in voltammetry to promote polarization. So ideal polarized electrode, the current does not vary with potential. So we have what we call ohmic potential and the IR drop. To create current in a cell, a driving voltage is needed to overcome the resistance of ions to move towards the anode and cathode. This force follows Ohm's law and is governed by the resistance of the cell, as you can be able to see there. So we have overvoltage and polarization sources. So overvoltage, the difference between the equilibrium potential and the actual potential. It develops because of polarization. So net result is you must apply greater potential before redox chemistry occurs. To add, sources of polarization in cells, that is one, concentration polarization. Rate of transport to electrode is insufficient to maintain current. So charge transfer polarization, magnitude of current is limited by the rate of electrode reactions. Other effects include adsorption and desorption. So types of voltammetry. We have different types of voltammetry. We have linear sweep voltammetry, as you can be able to see. Then we have staircase voltammetry, and also we have square wave voltammetry. We have also cyclic voltammetry. We also have anodic stripping voltammetry. We also have cathodic stripping voltammetry, and we also have adsorptive stripping voltammetry. So there are very many. Also we have alternating current voltammetry, and lastly we have polarography. So a variable potential excitation signal is applied to the working electrode. So different voltammetric techniques use different waveforms. Many other waveforms are available. Even Fourier transform techniques are in use. So you guys can appreciate Fourier transform. It is almost applied in many fields in analytical techniques. That is so instrumentation for voltammetry. You can see generally we have a waveform generator, then we have potentiostat, Then we have fast current to voltage converter. Then we have computer to display. Then of course we are not forgetting the working electrode and the reference, the cell generally. So instrumentation for voltammetry, the sweep generators, potentiometers, stats, cells, data acquisition, or what we call computers make up most systems. As you can be able to see, basic voltammetry system suitable for underground laboratory work. Then you also have the cyclic voltammetry cell with the hanging mercury drop electrode. So we will start with linear sweep voltammetry. So linear sweep voltammetry. So linear, it's performed by applying a linear potential ramp in the same manner as direct current polarography. So however, with linear sweep voltammetry, the potential scan rate is usually much faster than with DCP, direct current polarography. When the reduction potential of the analyte is approached, the current begins to flow. So the current increases in response to the increasing potential. However, as the reduction proceeds, a diffusion layer is formed, and the rate of electron reduction becomes diffusion limited. At this point, the current slowly declines. So the result is the asymmetric peak-shaped curve. So linear sweep, as you can see, voltammetry. A linear sweep what we call voltammogram for the following reduction of species A into a product P is shown. So you can be able to see the half wave potential is often used for qualitative analysis and can also be fitted. And then the limiting current is proportional to analyte concentration and is used for quantitative analysis. Then we have another one called hydrodynamic voltammetry, and it is performed with rapid stirring in a cell. What we call electrogenerated species are rapidly swept away by the flow. So reactants are carried to electrodes by migration in a failed convention and diffusion. Mixing takes over and dominates all of these processes. So most importantly, migration rate becomes independent of applied potential. So if you can just see hydrodynamic voltammograms, you can be able to see them. Different waves are obtained depending on the starting sample. Both reduction and oxidation waves are seen in a mixture, as you can be able to see. Then we have oxygen waves in hydrodynamic voltammetry. Oxygen waves occur in many voltammetric experiments. Here waves from two electrolytes are shown before and after spudging, or what we call degassing. So you can be able to see this first one and this other one. So heavily used for analysis of oxygen in many types of sample. In some cases, the electrode can be dipped in the sample. In others, a membrane is needed to protect the electrode. Then we have a Clark voltammetric oxygen sensor. Named after its generally recognized inventor, Leland Clark, originally known as oxygen membrane polarographic detector. It remains one of the most commonly used devices for measuring oxygen in the gas phase, or more commonly dissolved in solution. So the Clark oxygen sensor finds application in wide areas like environment studies, sewage treatment, fermentation processes, and medicine. By a thin solution of potassium chloride, as you can be able to see. The working electrode is a platinum disc cathode, as you can be able to see also, platinum disc cathode here. And a silver ring. We also have silver ring anode is the counter electrode. Several gases diffuse across the membrane, including oxygen, nitrogen, and carbon dioxide. Only oxygen is reduced at the cathode, and you can be able to see at the platinum the reaction that is taking place. So when a potential of negative 0.6 voltage relative to silver chloride electrode is applied to the platinum cathode, a current proportional to the oxygen concentration is produced. So the rate of electrochemical reduction depends on the rate of diffusion of oxygen from the bulk solution, so which is dependent on the concentration gradient. And of course you can be able to see everything there, how even the reactions at the both cathode and anode. So those are just general design and modern miniaturized versions. So hydrodynamic voltammetry as an LC detector. Of course you know what we mean here, so it can be used as a detector. Then we have cyclic voltammetry, what we know as CV. It is similar to linear sweep voltammetry, except that the potential scans run from the starting potential to the end potential, then reverse from the end potential back to the starting potential. So cyclic voltammetry is one of the most widely used electroanalytical methods because of its ability to study and characterize redox systems from microscopic scales down to nano electrodes. So as you can be able to see, the wave and the resulting IE curves. So the IE curve contain a large amount of analytical information. So for a simple system, hexacyanoferrate 3 and 2 ions, so can rapidly generate a new oxidation state on a forward scan and determine its fate on the reverse scan. So advantage of cyclic voltammetry is it has control rates, can determine mechanism and kinetics of redox reactions. Very important to note. So in the stripping now, the potential is scanned anodically towards the more positive potentials when the potential of the working electrode is sufficiently positive. The analyte is stripped from the electrode, returning to solution as its oxidation form. So magnitude of current of concentration of analyte. So magnitude of current of stripping peak is inversely directly proportional to concentration of analyte in mercury. The potential at which the stripping occurs is related to the redox potential of the analyte, and hence the potential of the current peak of the stripping step can be used to identify the analyte. So experimental conditions, of course, which must be carefully controlled if the results are to be accurate and precise. One is area of mercury film, electrode, or the size of the mercury drop when using a hanging mercury drop electrode. You also look at the deposition time. They also have the rest time, and we also have the rate of stirring, and lastly the scan rate during the stripping step. Very important for us to take note of. So molecular analysis, detection of the insecticide methylparathion using stripping square wave voltammetry with an electrode made from tetrasulfonated phthalocyanide electrode deposited on a carbon surface with a sodium ion sulfonated tetrafluoroethylene copolymer coating. I think those ones have some things you can see there. Yeah, you can be able to see methylparathion and so on and so forth. Then we come to now cyclic and spectroelectrochemistry. Cyclic, as we remember, cyclic voltammetry and spectroscopy can be combined by using optically transparent electrodes. This allows for analysis of the mechanism involved in complex electrochemical reactions. Example, ferrocene oxidized to ferricenium on a forward cyclic voltammetry sweep. Of course, ferricenium shows UV peaks at 252 and 282 nanometers. Reduced back to ferrocene can be fully reversible. We can also use scanning electrochemical microscopy. So scanning electron microscopy, scanning electrochemical microscopy uses nanometer size tips to probe surface phenomena. Analyses are run in constant height mode or constant current mode and can be combined with atomic force microscopy. So you can be able to see a typical system. here now. So some of the applications of scanning electrochemical microscopy can be used to identify precursor sites for corrosion in passive oxide films that protect metals. So the metal substrate is biased with voltage, and the scanning electrochemical tips detect the product of a reaction, providing an image of the reactive sites. Allow imaging of surface reactivity. Allow imaging of surface reactivity, as we have just discussed. So the instrumentation, as you can be seen, Princeton Applied Research. So these are just the instrumentation, and that is what we could be able to cover in this chapter. More reading you can see Scooge, Holler, and Koch, chapter 25, and many more. Thank you so much for listening.